I think we're going to break this discussion of distributed loads into two separate videos because we have a timer that times out at 15 minutes, and I don't want to talk too fast. So we'll get as far as we can, then we'll break and we'll go do a different video. So up until now, we have been talking about what you call concentrated loads on beams, a load that comes down in one place more or less. And a concentrated load could be any kind of load. There's kind of a fuzzy dividing line between concentrated and distributed, because look at that column is spread out across some area. But at some point we start thinking about distributed loads. And these are loads that are uniformly spread across an expanse of a beam. You might think of a concrete slab over some girders, or some wooden joists on a floor beam. Those are distributed loads. These are distributed loads. So thinking about the dividing line being fuzzy between concentrated and distributed, here is a box that weighs 50 pounds, and we could argue about whether we think that's concentrated or distributed. But whatever it is, we could draw a free body diagram of this thing, and look there, there's a pinned connection, and there's a roller connection. So we could draw a free body diagram. Oh, I didn't draw one, I just made a picture here. Anyway, I replaced that box with an arrow. Here's a load that's clearly distributed. It's kind of like that box in the previous slide, but it's spread out along the whole length of the beam, so it's definitely distributed. That box, or whatever it is, wave flooring, weighs 10 pounds per foot. And in this picture at the bottom, I have drawn a bunch of arrows next to each other. That is the symbol for a distributed load. And you don't have to make these arrows a certain distance apart or a certain height. They're not to scale, they're just a symbol. So you just make a bunch of arrows, there you go. So if you wanted to figure out some loads on this beam, and you wanted to replace this distributed load with one single arrow, how big would that arrow be? Well, this flooring, or whatever it is, weighs 10 pounds per foot, and it is 4 feet long. So it probably weighs 40 pounds. So I have replaced that distributed load with one single 40-pound arrow. Here's an example. I just thought you might find this interesting. Actually, two examples. These are out of the Steel Detailing Manual from AISC, the American Institute of Steel Construction. And what they are illustrating is how you could have a distributed load along your beam and replace it with a single arrow. Here on the right is a distributed load over half the beam, and they've replaced it with a single arrow. And what they point out is that that single arrow is in effect the resultant of all these little distributed forces. All right, well, let's look at this example. Here is let's say a deck or a floor with a balcony. It has some kind of flooring that weighs 30 pounds per foot, and it's got some kind of weight hanging off the end, 100-pound weight. So first of all, let's figure out how long is this beam. Well, we've got 8 feet from one end to the middle of the post, and then we've got another 4 feet, so that beam is 12 feet long. Okay, and that distributed load weighs 30 pounds per foot you have 12 feet. Each one of those feet weighs 30 pounds. So the first foot weighs 30 pounds, the next foot weighs 30 pounds, and you have, and you have 12 of those 30-pound foot chunks. So what is the total weight? That whole load weighs 360 pounds. How did we get that? I multiplied 30 pounds per foot times 12 feet, and I got 360 pounds. Here is my free body diagram. So up here in the left, there's my picture. Here on the right, there's my free body diagram. So I have replaced that distributed load with a single arrow, and I put 360 pounds over it. And then I replaced the two posts with reactions pushing up, and here's my 100-pound force on the end pulling down. So if this 360-pound load is the load of this distributed flooring thing here that weighs 360, how far is it from A to where I drew that arrow? And thinking about it, you might notice, well, you've already figured out that this thing is 12 feet long. So if that load is in the middle of that 12-foot beam, it must be 6 feet from the end. That's its location. Now let's figure out the reactions at A and B. And you rummage around in your toolbox where you have your 3 equilibrium equations, and you think to yourself, well, first, the one that will work is sum of all moments equals 0. And we're going to take moments around point A. Let me just say, we could just as easily have taken moments around B. We all kind of get in the habit of working from the left end and moving to the right, but we could have started at B. But we're going to take moments around A, and let's think about what directions those moments will go. That 360-pound force is turning clockwise, so that's a negative moment. Reaction B is turning counterclockwise, so that's a positive moment. And the 100-pound force is turning clockwise, so that's a negative moment. Okay? Now, let's use our equilibrium equation, sum of all moments equals 0, and we're taking moments around point A, so I put a little a next to that moment. And remember that the formula for moment is force times distance. Force times distance. Force times distance. All right, let's start chugging along. So the sum of all moments around point A equals, what have we got? First thing we come to is 360 pounds. It's 6 feet from the end, so there they are. And that's a negative moment because it's clockwise. Then what do we come to? We've got B. It's 8 feet from the end, and it's counterclockwise, so that's a positive moment. Then we've got the 100-pound weight. Be careful here, it's not 4 feet from the end, it's a total of 12 feet from the end. So 10 feet times 12 feet, and it's a negative moment. And what do those add up to? It's in equilibrium, it's not moving, so they add up to 0. Now, smushing some things together, I multiplied these terms so we know what numbers we're dealing with. Negative 2160, negative 1200, positive 8b. Smushing these two negative numbers together, we got negative 3360 plus 8b. We could add 3360 to each side. And when we do, we wind up with 8b equals 3360. Now we just have to find b. So let's divide both sides by 8. The 8's cancel out over here, and we're left with b equals this fraction, which turns out to be 420. So that post at B is carrying a load of 420 pounds. Or another way of saying that is that's the reaction at B. Now let's figure out how much weight is at A. And looking in our toolbox, we see here is sum of all forces in the y direction equals 0. Let's use that. So sum of all forces in the y direction, what have we got in the y direction? We've got A pushing up, so it's positive. We've got 360 coming down, so it's negative. We've got 420 going up, so it's positive. And we've got 100 going down, so it's negative. And what do those add up to? It's not moving, it's in equilibrium, so they add up to 0. Now, smushing the numbers together, we wind up with positive A, negative 40 equals 0. I bet you can easily see what A is going to be. And if you want to figure it out, you add 40 to each side. Those 40s cancel out, and you're left with A equals 40. So I'm going to write that under A. So look at that. What we found out was that A is only holding up 40 pounds, B is holding up 420 pounds, and then there's the load coming down and the 100 coming down. And that thing that we just did is surprisingly similar to the first assignment in your quiz. The numbers are changed, but the method is exactly the same. So I'll let you work through that in your quiz. Your quiz will step you through that. And just if you want to scribble it out on paper and check your answers, here are the answers you should get. You will find out that A is holding up 750 pounds and B is holding up 5850 pounds. And now I think for the next one we'll take a break here, and we'll come back in the next video and we'll look at